Well, dear students, today we'll discuss about the effect of disconnecting the neutral from a three-phase four-wire system. As we all know, the electric power is generated in a power station and it is transmitted over a long distance through transmission lines to various receiving stations, and then it is distributed to various substations which are located at various places and localities. The voltage is finally stepped down to 230 volts or 400 volts, like 400 volts for bulk consumers, and whereas 230 volts is used for general domestic consumers. The primary winding of the transformers that are installed in substations are connected in delta, whereas secondary winding of the distribution transformer is connected in star. The single phase two-wire system and three-phase four-wire system is generally adopted for distribution. The voltage between any two phase wires and the voltage between phase and the neutral is 230 volts, whereas voltage between any two lines is 400 volts. A single phase two-wire system and a three-phase four-wire system is generally used for distribution purpose. The voltage between any phase and a neutral is 230 volts, as I told you, and between any two lines or any two phases is 400 volts. So, single phase supply is used for a small, light loads like houses, small shops, but a three-phase four-wire system is used for large establishments like hospitals, industries, institutions. Okay, so the three-phase four-wire system is generally used for large establishments. Okay, here three-phase four-wire system, you have three wires, that's three lines, and fourth wire is nothing but your neutral. Okay, I will show you a single line diagram here. See here, you can see that this is a distribution transformer. The primary of the distribution transformer is connected in delta, whereas secondary is connected in star, and this is a neutral. Okay, this is ground. Neutral is grounded, and small establishments are connected between where light loads are connected between a neutral and a phase, whereas large establishment like your industries are connected between any lines and neutral. Okay, so this is the general layout of a distribution. Okay, now see this figure. Okay, the function of a neutral wire in a three-phase four-wire system is it serves as a return path for general domestic supply system. The neutral wire is always paired with each of the single phase load. So here in this figure, the alternator is connected to the load. Alternator, this is the alternator, okay, that is connected to the load, right? So see here, the neutral points, this is N1 is a neutral point of alternator, N2 is a neutral point of load. This is connected. Okay, the neutral point in both the alternator and load are joined together, right? The neutral wire serves as a common return. You can see this. The neutral wire serves as a common return for all the phases acting outward from N1. See here, this I1 comes here, right? Okay, I2 return path. See, I3 returns through this neutral. So this neutral acts as a return path, and suppose already you may be knowing about the balanced load and unbalanced load. In balanced load, all the three phases of the load having the same impedance and power factors. Therefore, the neutral carries no current at all, because the summation of all the three currents that are flowing in each of the phases are equal in magnitude. So the according to Kirchhoff's current law, the current and the neutral point is zero But in case of unbalanced load, what will happen? In case of what is called as unbalanced load? Unbalanced load is the one in which the load in all the three phases are not equal and may not be having the same nature, and the power factors are different. Therefore, the neutral wire carries the current. Okay, so neutral carries this difference of this currents in case of unbalanced load. This is the function of neutral wire. Suppose if this neutral wire gets disconnected, then what will happen? Let us see this. Let us take an example here. Okay, this is a three-phase four-wire system. R, Y, B are the three phases, and N is the neutral. Okay, and I have connected two lamps here. Okay, first lamp is connected between phase R and a neutral, whereas second load or lamp is connected between Y phase and a neutral. First lamp is rated with 100 watts, second lamp is rated with 150 watts. Both are rated at 230 volts only. Okay, 230 volts. Okay, the same thing I have written here. When a neutral wire in three-phase four-wire system is disconnected, the load which are connected between two line conductors and a neutral are get connected in series. If neutral is disconnected, these are get connected in series, and the potential difference across the combined load will be equal to the line voltage. This is now 230 volts, 230 volts. If it gets disconnected like this, then the voltage across these two will become 400 volt, will be equal to line voltage. What is the line voltage? 400 volts. The potential difference across each load is changed. Now the potential difference across each is 230 volts. But when the neutral gets disconnected, then what will happen? The potential difference across each load gets changed according to the rating of the load. According to the rating of the load, see here, the rating is 100 watts for this, 150 for this. When you calculate what is the resistance of R1 and R2, we will get for a lamp rated for 100 watts, resistance will be 529 ohms. For a lamp rated for 150 watts, the resistance will be around 352.6 ohms. Okay, and now what will happen? Let us see, calculate. Okay, R1 is, I have calculated like this. Okay, R1 is equal to, R is equal to what? V square by, P is equal to V square by R. P is equal to V square by R, right? So therefore R is equal to V square by P. P is 100 watts. Similarly, this is, so V is 230 volts. So V square by 100 we will get 529. R2 is equal to, so we will get 352.6 ohms. Now, when the neutral wire is disconnected, what I just shown in figure 2, the two lamps are get connected in series, and the potential difference across the combination becomes line voltage, that is VL is equal to 400 volts. Now what will happen? The current through lamp 1, that is I1, the current through lamp 1 is VL by R1 plus R2. I wanted to calculate what is the current through this. What is the current through this? V divided by R1 plus R2. What is V now? V is VL now, 400 divided by so and so. So how much you will get? 0.454 amps. This is the current flowing through I1. So because both are connected in series, the same current flows through both the lamps. Therefore, voltage across the lamp 1 is I into R1. So 0.454 into 529, which is equal to 240 volts, and voltage across lamp 2 is equal to 160 volts. See, you just concentrate on this. The voltage across first lamp has been increased beyond its rating, whereas voltage across second lamp has decreased. Okay, so how do you say this? The load whose resistance is large will have higher voltage. The load which is having a higher resistance will have a high voltage, and if this voltage rating exceeds the rated voltage of its load, then there are chances that this load may burn. This may burn. So you should remember that this is the effect of disconnecting the neutral. Okay? It is clear from the above example that if the neutral wire is disconnected in a three-phase four-wire system, the potential difference across high resistive load is increased and the potential difference across the low resistive load is decreased. In this process, the voltage across the high resistive load may rise more than the designed value. In this case, what was the rated value of each lamp? 230 volts. Okay, so lamp 1, when we disconnect neutral, when the neutral is disconnected, the voltage across lamp 1 has increased to 240 volts, which is more than the rated value. So what may happen? It may get damaged. It may get damaged. So this is the effect of disconnecting the neutral in three-phase four-wire system. Okay, so next video lecture we'll discuss about reliability. I hope you have understood this. Thank you.